Erythropoiesis is a very high-yield subject. It begins in the third week of development when blood islands appear in the mesoderm. So blood islands appear within the mesoderm, around the wall of the yolk sac. So within the center of these blood islands, there are hemangioblasts. This makes a ton of sense because blast means that you are basically producing something new, and hemangio means blood. So we're making progress here because we have a structure that is very important in the development of our blood. So this is all within the yolk sac, and this makes a lot of sense because that's where we first start making blood. Now by the 6th week, the intraembryonic hematopoiesis begins to take place in different organs. There is some overlap between periods of erythropoiesis, so there are often two organs producing blood at the same time. Erythropoiesis occurs in the liver from weeks 6 to 30, the spleen from 9 to 28, and the bone marrow from 28 onward. This should not be a huge surprise to you considering that you have learned conditions in which defects in the production of hemoglobin chains will cause hepatosplenomegaly due to expansion of erythropoiesis into the liver and spleen. Not only that, you can also have bone marrow involvement in places that are not the most active sites of erythropoiesis. For example, you can have cranial marrow involvement that causes a thickened skull. You can have facial involvement that causes a chipmunk-like facies. Remember, most erythropoiesis that occurs in the hip and the femur, very large bones. Can you think back to your hematology section and name a disease that this expansion of the erythropoiesis occurs into more bones and organs than you would expect? How about beta thalassemia? So let's use this pathology to understand the normal physiology. We can work forwards or backwards. Let's work backwards this time. So beta thalassemia is a defect in the beta globin gene, which means that your body will compensate with expansion of erythropoiesis to accommodate for the anemia that happens. So not only is fetal blood produced in different places than in adults, but you get composition of hemoglobin that is completely different subunits. So remember, fetal hemoglobin is alpha 2, gamma 2, while adult is completely different and is alpha 2, beta 2. So patients with beta thalassemia will have problems whenever they start producing this beta chain, which usually occurs 6 months in life, when you have completely stopped producing the gamma. Do you remember why it is important that they're different? Why the fetal hemoglobin has a gamma chain? Well, fetal hemoglobin has a higher oxygen affinity. But why? I mean, of course the baby needs oxygen, but why is it being so greedy with that oxygen? It's not. It's just that the way that the maternal blood interacts with the interface of the fetal blood. There is never any direct mixing of fetal and maternal blood. There is a very complex membrane that separates the two. So the maternal circulation comes by while the fetal circulation is coming by. And there's diffusion and transport of very important nutritional components. And there's also things that can cross, such as like IgG, that can cross across these membranes. What is important to know here is that on this side we have the fetal circulation, and on this side we have the maternal circulation. So deoxygenated blood from the fetus comes by these same venules in which the oxygenated blood from the mother is being delivered towards these same components, towards the same interface. The fetal hemoglobin has to be able to extract oxygen across these membranes. Remember, there is very deoxygenated fetal blood coming here, and there's very oxygenated blood coming here in the maternal circulation. The fetal hemoglobin has to be able to pull this oxygen from the maternal hemoglobin. The fetal hemoglobin has to be able to bind oxygen with higher affinity than the mother's adult hemoglobin to compensate for the lower oxygen tension of the blood that is mixed in these intervillous venules. Remember, the fetal blood components and the maternal blood components never mix. They are filtered and separated by the chorion, so somehow oxygen has to prefer the fetal hemoglobin binding sites instead of the mother's. So, can you tell me why fetal hemoglobin has a higher affinity for oxygen, besides that it's an alpha 2, gamma 2 instead of the adult alpha 2, beta 2? You are going to dominate boards if you told me that fetal hemoglobin does not have as much affinity for 2,3-BDG, which is 2,3-bisphosphoglycerate. So while this has a very strong affinity for alpha 2, beta 2 hemoglobin, there is very small affinity to the alpha 2, gamma 2. Now why does this make any sense? Well, 2,3-BPG is a byproduct of cell metabolism. Binds to deoxygenated hemoglobin to decrease hemoglobin affinity for oxygen. Does that make any sense? Yes. It binds free sites on hemoglobin. Remember, there are 4 sites on the hemoglobin molecule. So it will bind free sites. It'll bind here and here, so that these last 2 components that are holding oxygen will be released from the hemoglobin molecule to the tissue. So this makes a lot of sense, right? So if the cells in the tissue are undergoing a bunch of cell respiration, they're going to be producing lots of 2,3-BPG, because that is a byproduct of cellular metabolism. These tissues will be consuming a bunch of oxygen to produce this. And then eventually, you're going to be only in the glycolytic pathway, which will mean that you accumulate even more 2,3-BPG. 2,3-BPG will see a hemoglobin molecule that's partially saturated circulating around like this, and it's going to say, hey, I'm going to bind these sites so that you feel like you need to release this oxygen. And how convenient is it that 2,3-BPG is not only indicating that there's a lot of anaerobic metabolism going on, but it causes the hemoglobin molecule to release its oxygen. Even if it's not fully saturated, you still want this oxygen to be delivered to the tissues. And because fetal hemoglobin does not have such a strong affinity and does not allow 2,3-BPG to bind and make it release its oxygen, that is why it is able to bind oxygen with a much higher affinity than the maternal or adult hemoglobin. This concept of fetal erythropoiesis and fetal hemoglobin just tied together elements from hematology, embryology, and biochemistry. This is what examiners like to do. You have to be able to incorporate concepts and understand each with incredible detail, and then you can do really well in your exam and celebrate afterwards. So remember, the switch between fetal and adult forms of hemoglobin occur naturally and gradually, beginning at 30 weeks gestation and ultimately results in complete replacement of fetal hemoglobin by 6 months of age. So quick summary, let's discuss. Blood islands within the yolk sac are the original site of hematopoiesis, or are the original site of erythropoiesis. This will expand into the liver, weeks 6 through 30, then the spleen, weeks 9 through 28, and then the bone marrow, 28 and onwards. If you think about beta thalassemia, in which there's a deficiency in the production of the beta globin chain, then you get involvement of the structures that used to produce erythrocytes. So they can have hepatosplenomegaly, which is enlargement of the liver, enlargement of the spleen, and they can get medullary expansion, which means that on x-rays, their bones will appear particularly thick. And that is how you get expansion of bone marrow erythropoiesis. So that's a great example of how you can think through a disease and incorporate normal physiology.